Good evening. This is Math 2414. It's February 21st. A couple of announcements to start off class today. First of all, there's homework due on February 25th. I assigned a problem at the end of lecture on Monday, and I'll assign another problem at the end of lecture today for you to turn in on Sunday, or by Sunday at the latest. Exam 1 grades are posted on your D2L web gradebook. So make sure you go to that gradebook and look up your grade. If you want a graded copy of your exam sent back to you, please email me and I will respond with your graded exam. After today's lecture, there will be 2 more weeks, so 4 more lectures, and then it's spring break. So spring break's coming up rapidly. And exam 2 is the week after spring break. So the good news there is that you'll get the review for exam 2 before spring break, and you'll have it for a good 2 weeks, or pretty close to 2 weeks before the test. And one of those weeks, there will be no classes at all. So you'll have a lot of opportunities to get caught up in the class and to do some homework. I will be checking email and remind messages over spring break, and there will be some opportunity possibly for you to make an appointment to meet me in the WebEx office, and we can meet and answer some questions over spring break. I'll be around, and so that's something we probably can arrange. So, all right, so we are in the end part of talking about techniques of integration. That's what we've been looking at so far in Chapter 3. This is generally, most calculus teachers will refer to this as techniques of integration. And so we're looking at different methods that you can use to evaluate integrals, because remember what we've talked about is that integration basically is a more difficult process than differentiation. So we in section 3.1 looked at integration by parts. And remember that with integration by parts, you're talking about usually, not always, but usually multiplication is involved when you have an integration by parts problem. It can kind of sort of be looked upon as sort of a product rule for integration. It's not really a product rule, but at least it has some semblance of a product rule. Section 3.2, we looked at trig integrals is kind of the way we usually refer to that. And trig integrals, remember, we were talking more specifically about powers of sine x and cosine x and secant x and tangent x. All right, and so we looked at integrals and used trig identities to evaluate those kinds of integrals. Look at strategies that you could use for doing that. Then section 3.3, the section we're just coming out of, we were looking at integrals involving the trig expressions a squared plus u squared, a squared minus u squared, and u squared minus a squared. And the technique that we evolved for us for approaching those kinds of integrals was to use what we call a trig substitution. And we looked at several examples in lecture last time of trig substitutions to try to evaluate an integral that involves one of those kinds of quadratic expressions. So now in section 3.4, we're going to look at integration or integrals specifically involving rational expressions. Now we will look at a few that are not specifically rational expressions, not polynomials over polynomials, but they'll use the same techniques. And the technique we're going to use for integrals involving rational expressions is to use something called a partial fraction decomposition. Something that some of you may have talked about in a pre-calculus class, but I am going to assume that you have not talked about partial fraction decomposition. So I am treating this kind of like from scratch, that we're gonna try to look at this technique for in looking at integrals involving rational expressions. All right, so now what we want to do first of all is we want to look at some algebra for a minute, and then we're going to relate that back to calculus. So let's look at some algebra. Something fairly straightforward. Should be very straightforward, hopefully. If you have 2 over x plus 3 plus 5 over x minus 2, right? You have that rational expression, the two rational expressions that you're adding. Now you know that to add those together, at least I hope you know, that to add those two together, you need a common denominator. And so the first fraction, you'd use the equivalent fractions property and multiply it by x minus 2 over x minus 2. And the second fraction, you'd multiply by x plus 3 over x plus 3. Right? And we would get that the denominator would be x minus 2 times x plus 3. And then in the numerator, you'd have, just multiplying everything out and collecting like terms, you'd have 2x minus 4 plus 5x plus 15. And then we could finish by collecting like terms there, and we get 7x plus 11 over x minus 2 times x plus 3. Right? And so we took that addition problem, changed everything to get a common denominator, combined the fractions using addition, and got a single fraction at the end, or a single rational expression. Now, what I want you to think about is that, what we're saying here is that 2 over x plus 3 plus 5 over x minus 2 is equal to 7x plus 11 over x minus 2 times x plus 3. But it also says that the reverse direction also, and you don't usually think of it that way, but it's saying that if you started with 7x plus 11 over x minus 2 times x plus 3, that fraction could be split up into two fractions as 2 over x plus 3 plus 5 over x minus 2. And that is going to be important to us as calculus students for evaluating integrals. Now, this process of taking a single fraction and breaking it up into two smaller fractions like this is called a partial fraction decomposition. Kind of a highfalutin name there, partial fraction decompositions. Kind of sounds like a medical procedure of some type. But that's what we're talking about. We're talking about taking a fraction, a single fraction, breaking it up into what are called its partial fractions. Now think about what the ramifications are for this kind of problem with a integral. Let's say we had this integral, 7x plus 11 over x squared plus x minus 6 dx. Now that problem right there, is not a long division problem because the degree of the numerator is smaller than the degree of the denominator. It's not long division. It's not du over u because the derivative of x squared plus x minus 6 is 2x plus 1, which I don't have in the numerator. And so there's a lot of strategies that we've talked about that don't seem to really apply here. You could think about completing the square in the denominator, but it's not really going to be an arctangent because the numerator is not a constant. The numerator's got an x in it. So there, a lot of the techniques that we've talked about so far this semester seem to lead to a dead end in a problem like this. But now if you think about this for a second, the denominator factors is x plus 3 times x minus 2. And then notice that that expression, the 7x plus 11, sorry, over x plus 3 times x minus 2. And notice that we just decomposed that. We didn't really, but we kind of turned it around. And from the algebra we did at the top, we could rewrite that as the integral of 2 over x plus 3 plus 5 over x minus 2. like this, dx. And that composition, it makes the problem actually a very easy problem because both of those terms individually are just du over u. The 2 and the 5 are just constants that don't affect anything. And so we actually have the antiderivative very quickly. It's just 2 times the natural log of the absolute value of x plus 3 plus 5 times the natural log of the absolute value of x minus 2 plus c, and boom, you're finished. So this is what we want to talk about doing here, is taking a fraction that looks like this, that's or an integral that has a fraction in it that looks like this, where you have a polynomial in the numerator, and then in the denominator you have several factors, 2 or more polynomial factors. And the idea is, if we can figure out a process for decomposing a fraction like that, we might be able to evaluate the new integral. Now, the decomposition occurs in this step right here. In the problem we just did, it occurs in this step where we start with a single fraction and then we decompose it into these two fractions right here. Right, that's the partial fraction decomposition right there. And the question is, how do you go about doing that? Now, notice you can't really use the algebra I did at the top of the screen to do the problem, or to decompose, because I kind of started with the answer on that problem. I started with the decomposition. So the idea is, what if you don't know the decomposition? How do you go about actually going through that process? All right, so that's kind of laying out the groundwork for what we're going to do with partial fraction decompositions. Now, with partial fractions, there are 4 cases that we're going to look at. So partial fraction decompositions. Case 1 is where you have an integral that's in this form, a polynomial divided by linear factors. And let me actually rewrite that just a little bit. Distinct little linear factors. In other words, they're all different. All right, and so this is how we're going to deal with this kind of a composition. So the expression, the algebraic expression, is a polynomial in the numerator, and then in the denominator, you have distinct linear factors. So we might have something like this, ax plus b times cx plus d, and so on, however many linear factors there are in the denominator. And to decompose this, what we're going to do is we can break up a fraction like that into its partial fractions, and the partial fractions are all just going to have a different linear factor in the denominator. And you use one partial fraction for each linear factor. So you have ax plus b plus cx plus d, and in the numerator, these would always be constants. And I'm going to put plus dot 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 because it's however many linear factors there are. That's how you're going to decompose it. All right, so if the denominator is simply distinct linear factors, then you just decompose by writing a separate fraction for each distinct linear factor. And I understand if you're going through this video right now, trying to watch how this is working, you might be really unclear as to how this is going to work out in practice. But when we actually look at some examples, it'll start becoming more clear. All right, case 2 is you have a polynomial in the numerator, and you have in the denominator all linear factors, but at least one is repeated. So that means at least one linear factor occurs multiple times. So this is how we would write this. You have a polynomial in the numerator, and notice you've got all linear factors. So maybe you have a linear factor like ax plus b, and it's not repeated, but then you have another linear factor, cx plus d, and it's raised to the nth power, where n is some whole number. That's what we're talking about when we say a repeated linear factor. So the one distinct linear factor, ax plus b, you treat that just like you did in case 1. So that'd be just capital A over ax plus b. But then when you get to the repeated factor, what you have to do is you have to include a separate fraction for every power of that linear factor up to n. So notice I've got cx plus d to the first in one fraction. I have cx plus d to the second in a second fraction. Whoops, and the numerator should be a c there, sorry. So notice the numerators are distinct constants. So a, b, c, and so on. And I could, however big I have to go, so cx plus d to the third power plus ... and we could say n over cx plus d to the nth power, capital N over cx plus d to the nth power. So in other words, you just keep on counting with powers until you get to the actual power that's in the problem. So if the power is just a 2, then you're going to have 2 fractions in there. If the power is a 3, you're going to have 3 fractions in there for that particular linear factor. All right. We're going to write down all the cases, and then we're going to kind of take a survey of all the different possibilities, and we'll work through some examples. I'm going to show you some ways to approach these things. So case 3 is that you have a polynomial in the numerator, and in the denominator you have at least one irreducible quadratic factor. Now that means a quadratic factor that is not factorable. You can't break it down into linear factors. All right, so the case looks like this. It's a polynomial in the numerator, and let's say you have a linear factor, ax plus d plus b, but then you have a quadratic factor, cx squared plus dx plus e, that is not factorable. So that second factor is not factorable at all. You can't break it into linear factors. So you take capital A over the first linear factor. However many linear factors there are, you take care of them just like you've done before. But then the irreducible quadratic, there must be a fraction with that factor in the denominator. And then in the numerator, when you have a quadratic factor in the denominator, the numerator, it's possible that it is linear. And so you have to write capital Bx plus c like that. And that's how you decompose in that situation. Finally, case 4, and you could go on with these cases really forever, but these are the only cases we're going to look at with quadratic factors here. So case 4, you have a polynomial in the numerator. And then in the denominator, you have at least one repeated quadratic. And again, the quadratic has to be irreducible here. Because if it's reducible, in other words, if it factors, then you don't have case 4, you have one of the earlier cases, either case 1 or case 2. All right, so this case looks like this. It's a polynomial in the numerator. Let's say you have a linear factor and then the quadratic factor is raised to a power, and we're just going to say to the second power. That is absolutely the farthest we would go with it, is the second power, because these problems can be horrendous. So you have capital A over AX plus B. So we take care of that linear factor just like we've done all the other linear factors above. And then you kind of do the same thing that you did with a repeated linear factor. You need separate fractions for every power of that quadratic. So you'd have a fraction with cx squared plus dx plus e, and you'd have another fraction with cx squared plus dx plus e quantity squared. And in the numerator, you would need linear factors. So you'd have capital Bx plus c in the second fraction there, and then in the third fraction, you'd have capital dx plus e, like that. And however many of those kinds of fractions you would need. All right, so that outlines the cases, right? So now what we're going to do is we're going to actually tackle some integrals that fit into one of these cases and see if we can figure out a way to get through and actually figure out the decomposition. Now, to figure out the decomposition means to actually find all these capital A's, B's, and C's, and D's, and E's, and F's that are in the numerators of all these little partial fractions, right? That's what we're trying to do. All right, so let's tackle some examples now. So the first example, and so necessarily, we're talking at least at the beginning of rational expressions, and there must be more than one factor in the denominator. This is not going to work with just a single factor in the denominator. You need more than one factor down there. So notice in this integral, the denominator factors x minus 6 times x plus 1, like that. And so that's the fraction we're trying to decompose. Now the 10, by the way, is a constant. You can leave the 10 in the integral or you can bring it outside the integral. It really doesn't make any difference. I'm just going to leave it in. That just makes the most sense here. One less thing to have to worry about. So I'm going to decompose this fraction. And notice I'm going to do this in a separate color right here because this is scratch work, what I'm about to do. I'm going to decompose 10 over x minus 6 times x plus 1. And in the denominator, what do I have? What case do I have? Well, each factor is linear. They're all different. So these are distinct linear factors. This is case 1. This is case 1. All right, so case 1 says that you have a separate fraction for every linear factor. And then in the numerator, you just have capital A and a capital B like that. All right, and our job is to find the capital A and the capital B that force this statement to be true. Find capital A and capital B that force this statement to be true for all x. That's what we're trying to do. Then once we've figured out the decomposition, then we can return back to the integral. Okay. So there are actually two very distinct ways of dealing with this kind of problem. One way, so I really look at 3 methods for doing this. Not just 2 ways, but 3 methods. One is picking x values, and you'll see what I'm talking about in a minute. One is equating coefficients, and again, we'll do that on this problem also. And then finally, the third technique is a combination of these two. That is frequently suitable in longer problems. Okay, so what I'm going to do below is I'm going to do this problem 2 different ways. I'm going to pick x values, and then I'm going to equate coefficients, and so you can compare them. So picking x values right here, and equating coefficients over here. All right, so with picking x values, what you're doing is, first thing you're doing is you are getting rid of all these fractions here. So in our decomposition, we multiply this equation on both sides by x minus 6 times x plus 1. And we write down what we have when we get rid of all the fractions. So you get 10 equals a times x plus 1 plus b times x minus 6, like that, when you've cleared all the fractions. And now what you do is you actually pick x values, because what you're trying to do is trying to find an a value that forces an a and a b value that force this statement to be true for every x value. So what we do is we pick x to be equal to -1, first of all. And the reason why I'm picking -1 is because it makes x plus 1 equal 0. So when you do that, notice you get this equation, 10 equals a times -1 plus 1 plus b times -1 minus 6. So that's 10 equals a times 0 plus b times -7. And so notice what you get here. And I'm not going to do all that arithmetic all the time on these problems, but I wanted you to see where all this was coming from. So you get 10 is equal to -7b. And so notice what that gives you is it gives you b. But b's got to be -10/7. Yes, so yeah, we got one of them. We got b. And I usually put a box around it. Say, hey, I've got one of those values. And now you do the same thing again to find a. So in this case, we pick x equals 6. Right? And because 6 makes the other factor equal to 0. And what do you get there? You get 10 is equal to 7a. Right? And so the a is equal to 10/7. And what we have done is we have decomposed the fraction that's in the integral. So we know that this integral is actually going to be equal to a over x minus 6. So that'd be 10/7 over x minus 6 plus b, which is minus here. So this is minus 10/7 over x plus 1 dx. You know, and you've got du over u in both of those cases. The fractions are just constants that come along for the ride. And so in both cases, those are du over u. And so you have 10/7 natural log of the absolute value of x minus 6 minus 10/7 times the natural log of x plus 1, absolute value there, plus a constant. By the way, a lot of times in a textbook, you'll see the 10/7 factored out. So you have the natural log of x minus 6 minus the natural log of x plus 1. And so that's, you'll see textbooks frequently combine those two logarithms using the quotient rule for logs. So you have the natural log of x minus 6 over x plus 1, absolute value there, plus c. Okay, so that's picking x values and then decomposing the integral from there. Now, equating coefficients is a different way of doing the same thing, of finding a and b, but just algebraically a different approach. So you get rid of the fractions like we just did the other way with picking x values. So you get 10 equals a times x plus 1 plus b times x minus 6. But instead of picking x values here, what you do is you multiply all this mess out. So you have a times x plus a plus b times x minus 6b. And then you go ahead and collect like terms. So there's two x terms. You add those together. So that'd be a plus b times x. Plus, and then the constant term is a minus 6b. I'll put parentheses around the constant term. Now what has to be true here is the only way this statement could be an identity, the only way it could be true for all x values is if the coefficients of each term are equal to each other on both sides of the equal sign. So when I say both the coefficients on both sides, I'm saying that the coefficients of the x terms on both sides of the equations have to be equal. The constant terms have to be the same on both sides of the equation. They have to be equal. So look at the x term on the left side of the equation. On the left side now, not the right side, but the left side. And what you're saying right now is there is no x term on the left side of the equation, which is true. And so what's got to be true there? The x terms on the right side, the coefficient is a plus b. And on the left side, there is no x term, so its coefficient is 0. So you get a plus b equals 0. And then what about the constant terms? Well, the constant terms are a minus 6b and 10, and so those would also have to be equal. And so now notice what you get here is you get a little system of equations that you can solve. Now this system happens to be easy because the first equation you can just subtract b if you wanted to, and a is equal to negative b. And then you'd take that and substitute into the second equation. So you get negative b minus 6b equals 10, negative 7b equals 10, or b equals negative 10/7, just like we found in the first method. And since a is equal to the opposite of b, then a would have to be the opposite of this one, or positive 10/7. Right? And so you could get those right away that way. And then you go on with the problem like we did before. Now I know what you're saying. You're probably saying, if you've gone through this part of the lecture, you should be saying probably, well, that second way is a lot harder to do than the first way. I'm not going to do that. And I understand in a problem like this, yeah, absolutely, picking x values is the way to go. But there are going to be times when you may want to equate coefficients in a problem, and that may be the easier approach to the problem. So don't abandon that method and say, I'm never going to use that, because you'd be surprised. You might use it in some cases. Okay, so we're done with this problem. What did we do? We started with a rational expression at the very beginning. We identified that there were several factors in the denominator, and then we took off and looked at a decomposition of that rational expression. So we decomposed it into its two small partial fractions. And then what do? We found two different methods for calculating capital A and capital B, and in particular the capital A and capital B values that would force that statement at the very beginning to always be true for every x value. That's what we're after. All right. So let's go on to another example. And obviously we're going to look at a different case now. So let's say we have this integral, x plus 2 over x cubed minus 4x squared dx. All right, so the first thing to do here, you have a rational expression. It does not seem to fit any other pattern. It's certainly not du over u. It's certainly not a problem where you could divide it, because the degree of the numerator is less than the degree of the denominator. So it seems like a partial fraction decomposition might be an approach here in the problem. So you factor out an x squared out of the denominator, and you have x squared times x minus 4. Now x squared is not a quadratic factor. That's a linear factor that's repeated, right? And so this is case 2. X squared is a repeated linear factor. Right, because it's x times x. And so this is case 2. We have a repeated linear factor. All right, so we go to a different color here, because what are we going to do? We're going to do some scratch work. We're going to take the integrand, the expression we're trying to integrate, find the antiderivative for, and we're going to write out a decomposition for this. Now, first of all, you have this repeated linear factor, x squared. So remember, you have a separate fraction for every power of that repeated linear factor. So you have to have a fraction for x and a fraction with an x squared. The numerators are always constants in these cases. So you have a over x plus b over x squared. And then you have a third factor. So you have a third fraction here, which would be capital C over x minus 4. So there's the decomposition right there. And so now we are ready to tackle this decomposition and see what we can make of it. All right, so we multiply through by the least common denominator, which is x squared times x minus 4 over 1. Right, and when you do that, cancel everything out, you're left with x plus 2 equals a times x minus 4 plus b times x minus 4 plus c times x squared. Right? All the fractions cancel out there, and that's what you're left with right there. And so now what we're going to do is we're going to pick x values, right? We're going to use that approach here. There's some pretty obvious x values to pick here. We first of all pick x equals 0. By the way, x equals 0 frequently is a good number to pick, even if it doesn't make some of the factors equal to 0, because it makes the arithmetic so nice. So I said, when you pick x equals 0, you get 2 equals, the first term is 0, because there's an x in there. The second term is b times negative 4, and the third term is 0. So you get just 2 equals negative 4b. And so what do we get here? The b is equal to 1/2. I put a box around that. I celebrate. Yeah, right? Because we're going to celebrate because we got one of those constants. All right, so pick another x value. And another x value that makes sense here would be to pick x equals 4, because that makes 2 of the terms 0. So when you pick x equals 4, you get 6 equals 0 plus 0 plus 16c, because it's 4 squared times c, so that's 16c. And so you get right away that c is equal to 6/16 or 3/8. We are really making progress now. See, so look, you've got b and c. If you just get any old equation that involves a, b, and c, then you've got a also. And so I would, even though there's nothing obvious to pick, I'd just pick another x value. Absolutely does not matter what x value you pick here. You can make, you can make it a small number, a big number, whatever. Doesn't matter. All right, so if I pick x equals 5, and the reason why I might pick x equals 5 here is because I've got those x minus 4s in the expression, and so what is 5 going to make those equal to? It's going to make them equal to 1. So 5's not a bad value, but you could have picked any x value you wanted to here. It would have been okay. So if I pick x equals 5, I get 7 equals 5a plus b plus 25c. Right? And that's an equation that involves a, b, and c, but I've got b and c. So I can find a here. So this is 7 equals 5a plus b, which is 1/2, plus 25c. C is 3a, so that would be 75a. Like that. And so now we solve this for a. Now what I might do here is I might go ahead and get rid of all the fractions. Not a bad thing to do, I think. And I'm going to multiply everything by 8 to clear the fractions out. So you have 56 equals 40a plus 4 plus 75. Makes the numbers a little bit smaller, but it makes the fraction arithmetic easier. So you have 56 equals 40a plus 79. You subtract 79, and you get negative 23 equals 40a. And let me see, I think that's actually not right, is it? Because I'm subtracting 79 from 56. Let's see, so I think there might be a mistake in here somewhere. I'm looking for it though. And Jaime, if you're following along with the arithmetic, you might look at that too and see if you see a mistake in there anywhere. Okay, so I don't really see a mistake. 56, 40a, 8 times 1/2 is 4, 8 times 75a is 75, so that's right. Add the 79s there, all right, 4 and 75 and get 79. Subtract 79 and I get negative 23, which is right, equals 40a. And so a is equal to negative 23 40ths. And there's my other fraction. All right, and so now I'm ready to do the decomposition. So I can now rewrite my integral as a over x, so this is, negative 23 40ths, which is just a constant, so it has nothing really to do with the problem too much, plus b, which is 1/2 over x squared, plus c, which is 3/8 over x minus 4 dx. And even though that looks a lot worse than the original problem, that's actually a very, very simple integral. Because the negative 23/4 in the first term does not affect anything. That's just a constant, and so you have dx over x, which is just natural log of x. Second fraction, be careful, is the power rule. It's not a logarithm, because that's x squared in the denominator. So that's x to the negative 2. So that would give me negative 1 over 2x, because it would give me negative 1/2 x to the negative 1. And then the next term would also be another logarithm. So this would be 3/8 times the natural log of x minus 4, because that would be du over u also. And that middle term you could write as minus 1 over 2x. That would be fine. All right, but other terms are okay like they are. So the integral falls out pretty quickly here. You can see clearly that this is a tedious process, and so these problems can be lengthy. That's the main drawback to partial fraction decompositions. All right, let's go on to another example. Let's see how we've looked at case 1, we've looked at case 2. I bet you know what this case is going to be for this problem right here. So we have 6x over x cubed minus 8 dx. All right, and now at first it looks like there's just one factor in the denominator, but remember that's the difference of cubes, and so that denominator actually factors as x minus 2 times x squared plus 2x plus 4 dx. And what happens? It factors into a linear factor and a quadratic factor, and the quadratic factor is irreducible. It does not break down or does not factor again. And so this is case 3. X squared plus 2x plus 4 is an irreducible quadratic. And so this is case 3. All right, so we are ready to write this problem out and decompose. So you have 6x over x minus 2 times x squared plus 2x plus 4, like so, is going to be equal to, we take care of the linear factor, so that would be a over x minus 2. And then we have this irreducible quadratic. So the second fraction is going to be x squared plus 2x plus 4. But the numerator is going to be a linear factor. It's going to be bx plus c. Remember, the numerator, and if you have a quadratic factor in the denominator, the numerator needs to be a linear factor. All right, so what do we do here? We get rid of the fractions. So we multiply both sides of this expression, this equation, by x minus 2 times x squared plus 2x plus 4. So when we clear the fractions here, we are left with 6x equals a times x squared plus 2x plus 4 plus, second fraction, this would be bx plus c times x minus 2. All right, so you've got to find a, b, and c in this case. Got to find a, b, and c. All right, so it certainly makes sense here to pick x equals 2. If you pick x equals 2, you get 12 equals, and let's see, that would be a times 4 plus 4 plus 4. And then you're picking x to be 2, so you know this second multiplication problem is just bx plus c times 0. So that's going to go away. And so what do we get here? The 12 is equal to 12a. That's nice. And so you get that a is equal to 1. Yes. We've got one of the constants. And not bad either. All right, now another good x value to pick here would be to pick x equals 0. Because of that bx plus c, picking x equals 0 makes sense. So that would give you 0 equals a times 0 plus 4 plus, and then remember x is 0, so you have 0 plus c times 0 minus 2, right? Every place I see an x, I substitute 0. So that gives me 0 equals 4a minus 2c. But a was equal to 1, right? But a is equal to 1. And so I get 0 is equal to 4 minus 2c. So 2c is equal to 4. C is 2. And so now all what's left to do is to find b. And so, you know, you could equate coefficients if you wanted to try to find b here. Or you could go ahead and just pick another x value to find b. Since you've got a and c, another x value is going to give you an equation that involves a, b, and c, so that shouldn't be too big a deal. And it certainly doesn't make any difference what you pick here. I might pick x to be equal to 3 because that x minus 2 would just be equal to 1. So it makes it maybe ever so slightly smaller. Not a big deal here. So when x is 3, you get 18 is equal to a times 9 plus 6 plus 4 plus, and then bx plus c, so that'd be 3b plus c times 3 minus 2. And that 3 minus 2 is why I picked x to be 3. So you have 18 is equal to, let's see, so that would be 19a, and then plus 3b plus c. And then go ahead and substitute a equals 1 and c equals 2 into that equation. So you have 18 is equal to 19 plus 3b plus 2. So let's see, 19 plus 2 is 21. Subtract, you get negative 3 is equal to 3b, and you get b is equal to negative 1. Yes. And you've got the third b value, or the third constant value, which is b. And so now we're ready to go back to the integral. Here at the very bottom of the page, notice I'm not ready to integrate yet or to find the antiderivative. All I'm ready to do is write out the decomposition. So this would be 1 over x minus 2 plus negative x, c is 2, plus 2 over x squared plus 2x plus 4. right? And so, we still have a little bit of work to do here in order to evaluate this integral. Now, one thing is certainly the first term is just the natural log. The antiderivative is the natural log of x minus 2. And the second integral there, I might factor out a negative 1. And so that would give me if you factor out a negative 1, you'd have x minus 2 in the numerator over x squared plus 2x plus 4 dx, like that. Now, that is actually maybe not necessarily the easiest integral in the world just in itself. We've got some more work to do here. Now, it is not a partial fractions problem at the end because I don't have several factors in the denominator. Remember, in order to use partial fractions, you have to have multiple factors in the denominator. And so this is not partial fractions here. Instead, I think we're going to have to be more creative about how we deal with this problem. All right, so how are we going to do this? Let's go to the next page here. So I have the natural log of the absolute value of x minus 2. And then this is going to be minus the integral of x minus 2 over x squared plus 2x plus 4 dx. Now, it kind of sort of might remind you of a logarithm possibly, and so that might be a way to deal with this problem. So first thing we're going to do is we're going to split this integral up and put an x in this numerator, and then plus, because you've got that negative sign there, distributes through, so this would be plus, and then this would be 2 over x squared plus 2x plus 4. Geez. All right, so how are we going to do this? How are we going to do this? Well, in this middle term, if we let u be x squared plus 2x plus 4, the denominator, then du is 2x plus 2 dx. And all I've got is an x up there. So what I'm going to do first is I'm going to go ahead and multiply by 2 and a 1/2. Like that. And now I've got part of the integral there. And now what we're going to do, this gets to be really dicey here. You have to really watch what you're doing in this next step. If you're going to force this to be a logarithm, I've got this 1/2 out in front of the integral, and I've got a 2x. And what would I like the numerator to be? I'd like it to be a 2x plus 2. So I'm adding a 2 up there. That would force this to be a logarithm. But I can't just add a 2 in unless I also subtract a 2. Oh my gosh. So we have a minus 2 over x squared plus 2x minus 4, or plus 4 also, like that. dx. All right, so notice that really I haven't done anything at all to this integral. Because let's see, I've added a 2 there. I'm certainly going back through just to make sure that what I've got is right. You've got to really watch this and make sure that everything you've got is going to work out okay. But if you work your way backwards here, those are going to be the same integral right there. If you work the arithmetic backwards, you have to be able to see that this thing, when you do the arithmetic, would bring you back to the original integral. And in fact, it will, because when you add those two things inside the brackets, they'll just leave you with the 2x. And then you can take the 2 out, and it would cancel with that 1/2 in front there. So we would be okay there. So that's pretty tricky, that's for sure. And so and then you still have this integral sitting out over here. We'll deal with in a minute. We haven't even talked about this one yet. Very, very tricky to do. And so now, let's see what we've got. I've got minus 1/2 times this first integral. And then I distribute the minus sign, the minus 1/2 through, and so this would be a plus, and this is just going to be a 1 right here in the numerator. And what I just did is I multiplied a negative 1/2 times that integral, and then, but I left the negative 1/2 sitting out front, and then I multiplied negative 1/2 by that one, but I went ahead and multiplied it all out. And then you have plus, 2 over x squared plus 2x plus 4. And notice those last two integrals could be added together. So we're making progress. So we've got that integral right there, and that one's going to be ready to go now. That's going to be du over u. And then these last two integrals, I can go ahead and add them together, and I get 3 over x squared plus 2x plus 4 dx. And once again, you could, if you multiplied this out, you should get the original integral at the very top. If I did combine all the arithmetic here, I should get the original integral back when I do that. And if you want to, you could always check that. I would not blame you at all, because this is just really tricky here. And so check this. And so what do you get here? If you distribute the negative 1/2 through right here, you get negative 1x minus 1, right? Because you're multiplying through by negative 1/2 over x squared plus 2x plus 4 dx, plus, and then you have 3 over x squared plus 2x plus 4 dx. And then those two could be added together, and you get negative x plus 2 over x squared plus 2x plus 4 dx. And then you finally factor out the negative 1, and sure enough, you do get exactly what we started with at the very top of the page. I had to hesitate for a minute because I was even a little unsure that I was going to get that at the end there. So that means check right there. So that means I have done this correctly. And so now where are we? Well, now we've got the natural log of the absolute value of x minus 2, and then minus 1/2, and this next integral is a logarithm also because it's du over u. We've set it up purposely so that it would be like that. So it's the natural log of x squared plus 2x plus 4. And now we've got this last term, that 3 over x squared plus 2x plus 4. And the only technique we've got that might work there is to use completing the square. Take the 3 outside the integral if you want. And you've got dx over x squared plus 2x. And that would be plus 1, half of 2 squared. And then you have plus 4 minus 1, like that. So I'm still not done with this problem. I still have that last term to deal with. I'm going to go ahead and copy this. This is easily the longest problem we've dealt with, I think, this semester. And a little word of warning, it won't be the longest we do this semester, definitely. So you have the natural log of the absolute value of x minus 2 minus 1/2 natural log of the absolute value of x squared plus 2x plus 4. And then this last term would be 3. Finish completing the square. This is x plus 1 squared plus 3. Finally, that is an arctangent because you have u is x plus 1. Du would just be dx, and a would be the square root of 3. All right, and so you end up here with the natural log of the absolute value of x minus 2 minus 1/2 the natural log of the absolute value of x squared plus 2x plus 4. And then this would be 3 over the square root of 3, because you get 1 over a, arctan of x plus 1 over the square root of 3 plus c. 3 over the square root of 3 is equal to just the square root of 3. But believe me, I would be so happy if you got to this point of the problem. I would not have a problem with that at all. So, all right, so looking back, this was a challenging problem. This went all the way back to this page right here. Right, the decomposition happened a long time ago. We decomposed it, but then we ended up with an integral that, though there was something to do there, it was tricky to do it. There's no question about it. And so there was a lot of minefields in this problem that you had to try to step around and be really careful about. Now, I definitely don't want you to come out of this thinking, oh my gosh, all these partial fractions problems are going to look like this. That is definitely not going to be the case. But you need to be prepared for different situations. There's absolutely no question about that. So I kind of wanted to point that out. All right, so I do want to, let's see how we're doing on time here. So we're doing okay on time. I do want to work another problem. This one will be, relatively lengthy also, but probably not as lengthy as what we just did. But it is a different kind of example. So you have x squared over x to the 4th minus 2x squared minus 8 dx. All right, so definitely not something where it's du over u. There's no way that would work. It's definitely not something you would use long division on. Don't forget those two things at the beginning for fractions like this. You should always look for those first. Don't automatically opt for a partial fraction decomposition. For one thing, as you've seen, partial fraction decompositions are not a walk in the park at all. So they can be tough problems. The denominator on this one does factor as x squared minus 4 times x squared plus 2. Just a trinomial. And then the x squared minus 4 factors as x plus 2 times x minus 2. But the x squared plus 2 is non-factorable. So that's our irreducible quadratic in this problem. Okay, so this is another case 3 problem. To be honest with you, case 4, I just will probably typically never look at case 4 where you have a repeated quadratic factor. Those can be really tough problems. They're messy. So this is case 3 rather, sorry. All right, so let's write out the decomposition. So let's see where we are with that. So we'd have x squared over x plus 2 times x minus 2 times x squared plus 2 equals, so you take care of the linear factors, as we've seen before. So it'd be a over x plus 2 plus b over x minus 2. And then you've got to take care of that irreducible quadratic, so this would be cx plus d over x squared plus 2. All right, so we would clear the fractions. So we multiply by x plus 2 times x minus 2 times x squared plus 2, like that, right? Clear out the fractions. And so you get x squared equals a times x minus 2 times x squared plus 2 plus b times the x minus 2 cancels there, and you have x plus 2 times x squared plus 2. And then finally plus cx plus d times x plus 2 times x minus 2. Whew. All right, so let's go ahead and pick some x values and see how far we can get with that. So if we pick x equals 2, that would be good to pick. So we have 4 equals, and this would be a times 0 times 2, so that's 0, plus b times 2 times 2. No, that's not right. Let me back up there real quick. Sorry. So you're picking x to be 2, so that would be a times 0 times 6. That's better because that's 4 plus 2. Plus b times, picking x to be 2, this would be 4 times 6. And picking x to be 2, you'd have 2c plus d times 4 times 0. And so what are you left with here? Everything kind of goes away except that middle term. And so you have that 4 is equal to 24b. And so you get that b is equal to 1 over 6. So we get the first constant relatively quickly. So the x minus 2 has a constant of 1 over 6 in the numerator. All right, so another x value that would be good to pick would be to pick x equals negative 2. So if I pick x equals negative 2, I get, let's see, what do I get there? I get 4 again is equal to a times negative 4 times 6 plus b times 0 times who cares, right? Because it's 0. And x is negative 2, so you have plus cx plus d times 0 times negative 4. We don't care about the rest of that because those two terms go to 0. So you get 4 is equal to negative 24a, and so you get that a is negative 1/6. All right, so we're making progress. Now we have to find C and D. So you could continue to pick x values. That would be okay to do. So if you pick x to be 0, you get 0 equals, and let's see, if x is 0, you'd have negative 4a, and then plus 4b. And x is 0, remember, so then the c is gone on that last term, and you'd be left with d times negative 4, negative 4d. So dividing out of 4 there, you get 0 is equal to negative a plus b minus d, right? You're just dividing out of 4. And what do we know here? That a is negative 1/6, so this is 1/6. B is 1/6. And so that gives me that D is equal to 2/6. So D is equal to 1/3. All right, so we're making good progress here. Finally, we need to find C. So I'll just, to make the arithmetic simple, I'll just use x equals 1. At least the numbers are small there. And so you get 1 is equal to a times negative 1 times 3 plus b times 3 times 3 plus, and remember x is 1 here, so c plus d times 3 times negative 1. It's just tricky just to go through all this arithmetic. So you get 1 is equal to negative 3a plus 9b, and that's a negative 3 out there, so minus 3c minus 3d. Whew. All right, and so then you plug in the numbers that you've got up there. So you get 1 is equal to negative 3a, so that's negative 3 times negative 1/6, plus 9b, so that's 9 times positive 1/6, minus 3c, c is what we're trying to find, and then finally 3d, so this is 3 times 1/3. And so I get 1 is equal to 1/2 plus 3/2 minus 3c minus 1. And actually, so let's say you get 4/2 there, which is 2. And so you get 1 is equal to negative 3c plus 1. And so if you think about it, you get c is equal to 0 there. So that's good. You get c equals 0. There's nothing wrong with that happening. And it's actually definitely a benefit that we got that value like that. All right, so what do we end up with here when you use these coefficients here? You've got that the integral becomes and let me back up here again real quick here. That's a over x plus 2. So that's negative 1/6 over x plus 2 plus 1/6 over x minus 2 plus 1/3 over x squared plus 2. And that's actually not a bad integral there at all. The first integral is just a logarithm. That's du over u. So that's negative 1/6 natural log of the absolute value of x plus 2. The second term, also a logarithm, du over u. 1/6 natural log of the absolute value of x minus 2. That last term is an arctangent, where a is equal to the square root of 2, and u is equal to x. So the 1/3's out front, and then you have 1 over the square root of 2, 1 over a, arctan of x over the square root of 2, and then finally plus a constant. And so cleaning it up just ever so slightly, you get negative 1/6 natural log of the absolute value of x plus 2 plus 1/6 natural log of the absolute value of x minus 2 plus 1 over 3 square root of 2 arctan of x over the square root of 2 plus c. And for those of you who want to check your work, like with Wolfram alpha or something, they would very likely take those two terms and combine them. You could factor out a 1/6 there, and that leaves you with the natural log of x minus 2 minus the natural log of the absolute value of x plus 2. And so likely you would see those two logarithms combined using the quotient rule for logarithms. So you'd have 1/6 natural log of the absolute value of x minus 2 over x plus 2, like that. Ooh, man. So that problem works out relatively straightforward, but that's still, definitely a challenging way to deal with the problem, or a challenging approach to these kinds of problems. Now, what I want to do, I'm not going to work this example, but I do want to mention something at the end here. If you have a problem like this, I want you to be careful. Don't jump into partial fractions immediately until you've exhausted other possibilities. So in a problem like this, I see students frequently jumping into partial fractions here because they have denominator factors. But notice this is a long division problem, right? Because the degree of the numerator is bigger than the degree of the denominator. And so when you long divide here, I'm going to skip some steps, but when you long divide, you end up with 2x plus x plus 5 over x squared minus 2x minus 8, like that. And you see now you use a partial fraction decomposition on that last term, right? You've got 2x, whoops. You have 2x dx right here for that integral plus, and then this integral is x plus 5 over x minus 4 times x plus 2 dx, and that is now actually a relatively easy partial fraction decomposition. So you had to deal with long division first, and then go from there. And so I'm just going to put etc. there for you to finish that out. All right, so let me give you the homework that's due on February 25th. So let's see, homework on next page. I've done a pretty minimal requirements for the homework. 2 or 3 problems is typically what I'm going to ask for each Sunday. And so this is the homework that's due on the 25th of February by midnight. And so in section 3.3, which I had already assigned this problem before, but section 3.3, this is problem number 138. That is going to be a trig substitution problem, number 138. And then in section 3.4, partial fraction decomposition, I want you to look at problem number 212. All right, so you've got those 2 problems to turn in this week. I've got the link up in my Google site for you to turn it into my Dropbox account. All right, any questions? I guess not. Jaime, you must be pretty stunned.